cups, and you shouldn't have them in there, and lollipop, yada, yada, into lab debris. That's expensive waste to take care of, okay? And so, be kind. And think about the environment. Don't put these chemicals into the regular trash, okay? All right, so the first lab we're going to do is called the smells lab, or the smell lab, I guess. And the idea of this lab is that we want to connect molecular shape to biological function. So in this case, the biological function, the readout of this experiment, are the receptors in your nose, okay? And these receptors will bind to odorants, sense organic molecules, most likely in the air, maybe not always organic, and when those bind to these receptors, they make specific molecular interactions with these receptors, and this leads to a signal, a neuronal signal that goes to your brain that perceives a particular smell or odor. And so that's a great sort of way of learning about molecules and their structures and their shape and stereochemistry. And so we want to construct some general hypotheses. And the kinds of hypotheses I like to think about is, well, what about functional groups? Functional groups. So imagine we had an organic molecule, and we'll get to thinking about how we draw organic molecules in a minute. But imagine these are different atoms that are connected together, and we could have a variable R group here, or functional group here. This could be, you could consider it a variable group. And so, one thing to think about is that maybe different functional groups on different organic molecule scaffolds could lead to different types of smells. And maybe the smell receptors look for specific functional groups. That's one possible hypothesis. Another hypothesis would be that molecular shape defines sort of the way in which a molecule would interact with its three-dimensional receptor. Or maybe it's a combination of both how functional groups are specifically read out and their molecular shape. So these are the things that you want to think about. And so, ultimately what we want to do is test this hypothesis by, smelling different chemical compounds, looking at their structures, and then, thinking about what they smell like, using a word bank to keep it kind of simple, and then compare how different molecules smell and what their structures look like to determine what types of hypotheses make sense for that particular scent. And then reformulate your hypothesis. And all right, so in order to understand molecular structures, we need to understand bonding and valence electrons. And it's a bit of a review, but apparently to bring everyone up to speed, it's important to do this in years past. So if we think of a hydrogen atom, we think of a hydrogen atom as having a nucleus, a proton, and a neutron, and in its valence shell, which hydrogen has a very simple single 1s valence shell, we write out the notation 1s1. And this means the first s orbital, and it has one electron. So here's another way to say electron E minus. So this is our hydrogen. And if you go up one atom in the periodic table, you go to helium, and it has two electrons, so we say 1s2 for our notation. And we know, of course, that helium is a very inert gas and a noble gas, and that's because its outermost valence electrons, this outermost orbital, which is the first s orbital, is full and occupied. And that's because the maximum number of electrons you can put in an s orbital is 2. Okay, so now we have a carbon, which is our favorite atom in organic chemistry. And it has a full 1s orbital. Then it has 4 electrons in what we call the p orbital. And two electrons in the second s orbital and 2 electrons in the second p orbital. So it's 1s2, 2s2, 2p2. And so since the s and the p orbitals are both in the second shell, then you have 4 electrons total in the total valence electrons. And these are basically going to be able to do bonding interactions because you do not have a full outer shell for the second shell, which would be 8 electrons. And remember your octet rule, that a full outer shell would have 8 electrons. And then we have oxygen. There are many other examples that you can look at in your exercises and sapling, and I'm just trying to give an intro. And oxygen has 2 more electrons than carbon. So you draw it like this: 1s1, 2s2, 2p4, 2, sorry. 1s2, 2s2, 2p4. So there's 4 p electrons, and so in that outer shell there's 2 plus 4 electrons, that's 6. And that's just 2 off of that octet, okay? All right, so now we'll get into bonding, and we'll do something very simple. We'll do methane. So imagine we have a carbon. And now I'm going to draw this in a very simplified way. I'm not even sorry for people that drew that circle. I'm just going to draw the valence electrons. For carbon, I'm going to draw them in black. So remember that the valence electrons are only these second shell electrons. There's 4 of them. There's 2 in the s and 2 in the p. They'll hybridize into these special molecular orbitals and interact with hydrogen in methane. And each hydrogen has 1 electron. Remember that when we're bonding, we're sharing electrons between 2 atoms. Because see, hydrogen has this extra electron. It would like 1 more to fill its shell. Its outer shell, the first shell, would like 2 electrons. So it says, oh, carbon, you have an extra electron. And carbon wants an extra 4 electrons to fill its outer shell. So it says, 4 hydrogens come here, and you get 4 bonds, and you get methane. Okay. So, and then the molecular formula comes out of this. This is methane, natural gas component, the principal one. And, it has 4 bonds. That should be pretty clear. So, we might not always want to draw it in this longhand Lewis structure approach, and we might want to draw it in a simpler one. And so this is what we call bond line notation, where each line between adjacent atoms that are bonding signifies 2 electrons. So there's 2 electrons in each one of these bonds. So we call this bond line notation. And on sapling, you'll play with all of these types of drawings of molecular representations. Okay, so it should become immediately obvious that there should be some rules for constructing molecules that have no net charge. Okay, so with no net charge. So carbon is right here, has 4 bonds it can make, okay? And nitrogen, which I didn't draw yet, can make 3 bonds. Oxygen, 2 bonds. Halogens like chlorine, fluorine, bromine, things like that can make one bond. And hydrogen, one bond. Okay, does everyone understand why that's the case? I mean, don't just memorize these rules, but know the underlying principle. The principle is this, that carbon only has 4 valence electrons in the second shell, and 4 minus 8 is 4, so it makes 4 bonds. It's one way of thinking about it. But it has basically 4 electrons it could share, and if it shared those and received an electron back, then it would fill its octet and satisfy it. Whereas nitrogen has 5. Okay, so nitrogen looks like this, and this is a lone pair. Lone pairs are generally happy, and they don't really need to do any bonding. They can do special kinds of bonding, but not covalent bonding. And so if you're going to make, say, ammonia gas, then it's going to be NH3, and it's going to make 3 bonds, okay, because you have that lone pair. Oxygen's going to have 2 lone pairs, so it's only make 2 bonds. Halogens have 3 lone pairs, so only make 1 bond with that extra electron. And hydrogen, of course, we've talked about. Okay, so we'll do a little bit more on bond line notation to make sure we understand it. So, just starting out with something very simple, we'll do ethanol. And this is a good way of drawing out ethanol. Its molecular formula is C2H5OH. It's one way of doing it. One could maybe do it like this too. Just count up your hydros, count up your oxygen, count up your carbons. And then what you want to do is make sure that you just satisfied all those rules that I just told you about on the previous page. The carbons make 4 bonds. So, you go around and, count 1, 2, 3, 4. This carbon has 1, 2, 3, 4. The oxygen has 2 bonds. Maybe we'll highlight our oxygen like this. And our hydrogens all, of course, make 1 bond. Okay. And then the other thing that's important to represent are your lone pairs, which are shown here on your oxygen. So this is one way to draw these things, but of course, when you get more involved in organic chemistry, you might want to develop some shorthand notation. Because really, we know already now the carbon makes 4 bonds, so if I just look at the carbon-carbon bonds, I could, I could draw it like this, and I could say, oh, well, those hydrogens are implied, but I don't even want to draw out the carbons. Really, for shorthand notation, I just want to draw lines. And the nodes of these lines, when these lines change angle, the direction of the pen changes, then I know that there's a carbon at that node. There's a carbon at the node. Okay, and there's more than just a carbon there, because I know that I have a carbon-carbon single bond. I need to have hydrogens around there. So really, if I were to think about this, is, there's 3 hydrogens there. That's how I get 4 bonds. Then I go to a CH2, and then I go to an OH. So this, though, here is the shorthand notation that you'll commonly see in organic chemistry textbooks, and you should become familiar with. So we can think about another one. We have double bonds in carbon, like vinyl chloride. And C2H3Cl is its formula. So it looks like this. If we were going to draw it in the shorthand notation. And so then what you'd want to do is count your bonds to figure out where the hydrogens are going to go. So now I have 1, 2, 3, 4, and then I have 2 hydrogens over here. So I'll have 1, 2, 3, 4. So that's the basics there. And here with vinyl chloride, this is a monomer that's used to make the plastic that you find in like shower curtains and garden hoses and things like that, polyvinyl chloride. And so these will daisy chain together into a polymer. And so this is the basics. These are the basics here for understanding molecular representation. So I wanted to actually, I'm sorry, I want to insert a. Let me have that. Okay, I want to insert here a slide on stereochemistry, which I regrettably didn't add to our notes template. And the idea of stereochemistry is that these molecules are 3-dimensional, and these bonds are actually pointing in all different directions. And if you have a molecule that, that has 4 different groups around it, and I could draw them as X, Y, and then out towards us, Z, and then out of plane here, we'll call this W. So if I have a molecule, and I have 4 different groups around it, around the central atom, we would say that the central atom is chiral. So these X, Y, Z, W, those aren't atoms. Those are sort of algebraic representations for different types of functional groups that could be displayed around this particular atom. And the reason that it's chiral is that if I change the position of any 2 of them and swap them, that the molecule is not superimposable on itself, okay? That would be a completely different 3-dimensional object. And that might be better illustrated with an example. And something that we'll be using in class is lactic. We'll do, an important biopolymer is made from this monomer called lactic acid. It's used to make a biopolymer called polylactic acid. And this is a plastic PLA, and you'll find it in these biodegradable plastic cups and things of that sort. And so the idea is you have a central carbon that's chiral, and it's surrounded by 4 different groups. So we have a carboxylate here, a hydrogen out of plane into the back of the paper, a hydroxyl coming out towards us, and a methyl group around a chiral carbon. Chiral carbon is here. And imagine you had a mirror here, mirror plane, and this thing we're looking into the mirror. So here's a mirror plane. These are 2 different 3-dimensional objects that are not superimposable, and you have to use your spatial reasoning abilities and rotate these around in your head. And as you rotate these around in your head, you'll realize that the only way that they're superimposable is if they were a mirror image of one another. And mirror image things are not superimposable. We call this the R stereoisomer, and this is the S, and these are enantiomers. Okay, so that's our stereochemistry. Hopefully everyone, maybe I'll have a little bit of time here to do. We won't do all these slides. We'll just do the last one here really quickly. Is everyone caught up? I'll post these notes too once they're filled out. So the idea is that different molecules can be represented as these line bond notations. You could represent them as a collection of sticks. In say a molecular graphics package, you could have So this particular molecule here is an ester with an alcohol chain on it. It's called it's a butanol chain on an acetate acid, and these are condensed and water is released, and you get this ester, and it has a fruity odor. Okay, and one could draw this in this representation, or show it in a stick drawing here, where the oxygens are red and the blue atoms are carbons, or one could represent it in this space-filling depiction called CPK. Okay, and CPK is named after Corey, Pauling, and Colton, and what they're showing is what's called the outer van der Waals radius, where those outer edge electrons are positioned. So this is actually the real three-dimensional shape of this molecule. It looks like this. And the way in which we figure out what the van der Waals radii of molecules are is we do things like X-ray crystallography. We crystallize a molecule, or we use various other methods like measuring their mechanical properties of gases, measuring the critical point, and doing refractive index measurements. And we can figure out exactly how close these molecules can pack next to one another, and that tells you what their van der Waals radii are. And so when you have basically the smell, this odorant, and it's going into your nose, you have a protein receptor in your nose that's going to see this three-dimensional shape. It's going to recognize it and form a complex, okay? And that's going to lead to a signal that's propagated to your brain. And so if it has the wrong molecular shape, it won't fit into that receptor in your nose. And so that's how it works. And so the last point I want to make, is that you get remarkably different outcomes when you smell things. So when you smell this, compound at the top, this butyl acetate, it smells like, a fruity smell in oranges or apples. If you take butanol by itself, 1, 2, 3, 4, this is butanol. It smells very alcoholic. It smells kind of sweet, kind of an alcoholic, harsh odor. But if you change this molecule to an acid, okay, and this is butyric acid. This is a smell of, the BUT part of the word gives it away. It's a smell of rotten butter, okay? And it turns out that butyrate itself isn't so dangerous. It's actually completely non-toxic. And, microorganisms in your intestinal tract make butyrate all the time, and your intestinal cells use it as fuel. But, the smell might, you associate with this. It's a very harsh, sort of rancid sort of rotten butter smell. But what I'm trying to point out here, besides the odors and the remarkably different outcomes you get, is that you're changing these functional groups from, in this case, an alcohol, OH, or an HO, to an acid, COOH, okay? And so these different R groups give you remarkably different smells, okay? And I'll have to end there. I can't really tell you much about the biology, but this is a chemistry class, and you can talk to me in office hours if you're interested.